Draft physics video. Yeah, it's been a while. Sorry. Yeah, just a lot of other stuff I've been working on. But you know, every dinner I watch a physics lecture. Um, so I'm staying in the game. I'm thinking and working on stuff. Just really have to work on the credibility issue to be able to make the contention that they've sort of got it all wrong. So I thought I would talk about the dimension thing, the 3 dimensions and the whole movement thing and the perpendicular thing, because it's really quite important. Ironically, well, interestingly, it's not really ironic, I suppose, but going in, I thought the particle part of the gravity thing was really big. That's really interesting. But, the really interesting bit is the time dilation element, the relativity element, because it's an actual physical thing, and it manifests into this idea of velocity of matter causing this polarization, which causes the magnetic and electrical charge phenomenon. We're kind of stuck with the words we have, and the connection between electricity and magnetism has this element, like we call it charge with electricity, but we don't really call it anything with magnetism, but in a sense it's a form of voltage, velocity of electrons that it's a current. And anyway, so I thought of a simple way of drawing this, so I just figured we'll do some of this simple way of drawing it. So the idea of something moving matter in 3 dimensions. So a simple way to draw 3 dimensions would be just to do, up and down and left and right. And then to understand, in the middle you have forward and back, with this little X thing. It can be arrows or however you want to look at it. And so the idea would be, the other 2 dimensions are quite simple. I mean, indistinguishable almost. You can rotate them in any way you would choose from the perspective of the forward-back dimension. And another way of looking at this is when matter is purely, truly stationary, a piece of matter, it means that the elements inside of it are all balanced. So each one of those arrows would be exactly the same length. So just assume that each one of these arrows is exactly the same length, and that this middle, forward and back, would also be the same length as these arrows. And that would be something stationary. And you can sort of see the idea of a circle, and then this traversed circle that would go this way, completing the sphericalness of 3 dimensions. But from the perspective of the thing, if it could have a perspective, that this spherology is just in kind of almost layers, almost like an MRI or something, and they're kind of, in a sense, vacuous, but I mean, they're just not as real as you would think. So anyway, the point I wanted to make with this diagram was, I suppose there's other ways to draw it. I could do it this way. I suppose this might work. And then you could see it more realistically, I suppose, if you can get that this is forward, this is sideways, and this is up and down, this is sideways, and this is forward and back. Now the point is, when matter's stationary, all these lines are even, but they're not real lines. I mean, obviously there's all these little things in between. So when there's a velocity in a conductor, so if you have a conductor and electrons are moving through it, the magnetic force is perpendicular all the way around. I mean, it's going this way, this way, this way, this way. It's all the ways, so it's not fixed. The dimensions are just the distinction between barriers, but where exactly those lines are doesn't really matter. It's just the difference between 90 degrees and 180 degrees. But anyway, or 180 degrees and 360 degrees. So anyway, just thinking about it. So when matter is moving, so understand that the matter is just made of these elements that are moving, and they get trapped in orbits, so to speak. The individual thing doesn't actually do the orbiting. It's just that there is an element that'll always be fitting into a location that will create the idea of an orbit, and they're trapped in the orbit by this gravity force that's, through polarization, is magnetized, so it can be stronger. But the point is there's the force is blocked, consumed by the element getting its direction changed, so to speak, and the absorption of this element, in the sense that the element is actually absorbed. The element, that means that this thing actually moves this way, and then it goes back to moving this way again, and then it moves this way, and then it moves that way again. So it's all this aleasing. So again, it's like when the planet Earth is going around the sun, the elements inside of it aren't doing a circular path, they're doing an aleased path. They're moving in different dimensions. You know, they go left one, they go two forward, they go one left, two forward, that kind of thing. I don't know if that's, I mean, it's what I've said is accurate. I just don't know if I said that in a way you can understand. But the point is that the element of force is absorbed in the sense that it is used, and that means it doesn't arrive here at the time it was allotted to for balance, and so then there's an imbalance for some moment of time, and that allows this thing to move in the likewise interior towards direction, the nature of attraction. And repulsion is built out of the same thing, just reversed and polarized. So anyway, what the point is that all the elements are moving the speed of light. So the only bits moving inside of you, the only part of my hand that moves, are the little bits that make up my hand. My hand doesn't really move. The little bits move, and the collective that is my hand goes where the bits go. I mean, they're the driver. They're the mechanism. My hand is not the mechanism. My hand is not the machine. The machine is the little bits, and it's the destiny of the little bits that decide the destiny of the hand. The bits come first. The hand is a byproduct. Alright, so I'll get to the thing, the point, the realization of an image here. So here we'll take again this simple idea of this equal tangent. So now you're moving forward. Let's say you have velocity in this forward direction, so coming towards you out of the paper, and so your arrow is getting longer coming out, and then it is going in, kind of a thing. But realistically, what's also happening as this proportion changes is the real change is these arrows have to get shorter. So if you think about as you're moving faster and faster, you're moving closer, you're moving more speed of light in one direction than any of these other directions. So I've sort of said this before, but and this is something even some physicists will acknowledge, is that mass is a product of this energy having a directionality. So they sort of understand that if you put a bunch of photons, if you could capture some in a box, that they would have a mass in the sense of where they're going. In the direction they're moving, they have mass. They don't have mass in any other directions, just in the direction they're moving, just in one dimension. And so as something moves faster towards you, you can kind of visualize the idea that the mass, the force of the thing in the other directions, has to diminish. It has to, and it can only diminish by becoming less, like it has to be physically less, or it has to kind of timeshare, where it just doesn't do that part as often. So the stuff going this way, or this way, or this way, or this way, doesn't go in those directions as often. So if 10 of them move to the left in 10 seconds, 5 of them move to the left in 10 seconds. So all you do is change the amount of mass moving in that direction. And that allows you to go faster in the forward direction, because this is essentially all drag, right? I mean, you can sort of understand that this is all drag. These are all going the wrong way. You're trying to go the speed of light. You're trying to go fast forward, let's say approaching something like the speed of light, or you're heading that way. And what's slowing you down is the fact that you have pieces of you that keep going this way, and this way, and this way, and this way. And those pieces aren't going the right way. So they're taxing, they're using up time going the wrong way. And that use of time going the wrong way has to slow you down. You can't leave them behind, because they're what forms your hand, for example. So all you can do is have them blip, have them go to sleep, take a lot of little naps. I don't know what other metaphors to use, but kind of disappear for a minute, and then have some mechanism like a filter outside the shell that it can be reintroduced. So it leaves in the sense that it goes into the ether or vapor around something, but that vapor drags it back so that it will show up again. So it's like it creates a world where you can have identity retained, information retained, and put back into the system so it retains a structure, but the element isn't in the matter the full period of time anymore. It's only in it for a percentage of the time. And so that percentage gets less and less as you go faster and faster. Then more of your identity is in that. I should explain that more clearly, but let's just say that the idea of an atom is just a swirl, or an electron, let's just call it an electron. It's a storm, it's a tornado, so to speak, of structure. And it's balanced, essentially. But what it has going around it is another field of less coherent, less concise, but still, say, spinning in the right direction. And so an element that has this spin pops into this other spin, goes around, and at a certain period pops back in. So you have an element going this way, it leaves essentially, but its identity is retained. The information of what it is retained, and because of the precision of the mechanism, it will be reintroduced to recreate the amount of this, to create this again. So it's not like it's lost. It goes to the field brings it back. So it doesn't lose it, it just lets go of it for a while, and then the field will bring it back. And so as matter accelerates, more and more of the matter's identity isn't in this matter anymore, because this matter's, it's doing this one arrow thing. It's lengthening the forward arrow. So most of the matter's going this way, but most of the identity of the other dimensions are here in this field, in the close field, and it's still retained. So the field becomes heavy with these other two dimensions of motion, and as the matter becomes light in those dimensions. I think that's an okay way to say it. So it's like it's as if the matter was expanding. So it's, in a sense, this matter expands, gets much bigger, but it's able to retain the left, right, up, down dimensions in this larger structure, and then when it slows down again, it would go back to its normal size. That kind of a thing. Alright, and so that is I think a simple way to visualize. I also did with like a square, a box. Let me just look at my I didn't really complete that one, but it's like you could take a cube, and then you could understand that if the cube was going in one direction, the one face was essentially is getting larger, okay, in the dimension you're going in, and the other faces are getting smaller. So the cube gets smaller except for the face that's in the direction you're going. So as you move, the cube distorts, and the forward face becomes bigger and bigger and bigger with velocity, and your perpendicular space becomes smaller and smaller. But what's really happening is the field around the space still retains the balance of your original structure. How long it retains it, I don't know. That's another subject. Especially when you start going really fast, the whole thing probably does break down at some point, and you just become photons going in one direction. All your mass is just converted into a stream of energy. Alright, so the other part to this is the idea that if you have something that's let's say these forward and back dimensions, left, right, forward, back, are broken up time-wise, and that the only thing going that's not broken is the direction you're going in. The idea is that as gravity comes in here, so as the field force goes through this perpendicularly to the direction you're moving, so you're moving in this direction with a velocity, the perpendicular dimensions are less material, and they're basically turning on and off. They almost have a frequency, you could almost argue. They're on and then they're off. They're there, they're not there. They're there, they're not there. They go from being part of the matter to being part of the field, part of the matter, part of the field. And as that's happening, that I think is the nature of polarization, because it allows for far more absorption. Because with every exit of the release of one of these elements in the perpendicular dimension, it gets released to do this. So to do this acceleration, you have to release some of this. And as you release that, you're releasing it from the interior. And the interior structure demanded a polarization, a directionality. It's more structured. So it's polarized. So you're releasing polarized. And so what's coming in is unpolarized. And so when it gets replaced, so here's the blip on, and then, okay, the blip off, it releases. Then when it blips back on again, it's absorbing these arrows again. And then it's going to release them again. And so every time it absorbs them, they become polarized, and then when they're released, they're polarized. And so that's why the field energy is polarized by electrons moving with a velocity. So anytime an electron has a velocity, the electron is releasing quanta, energy, field, and it releases it polarized, and it absorbs it unpolarized. Something like that. And so that's what creates these fields of magnetism and charge. Okay. And also the fact that whatever in this field would already be polarized coming in would make it more effective at being absorbed. So that's the nature of the sensitivity, is the same thing as what you're producing is also true of what you're consuming. So you'll consume more readily, you'll absorb more readily polarized than you will unpolarized. Right. So the only other part to explain, again, well then you're back to the magnetism argument, in which again you have to, I've already explained it, but it's the nature of the polarization being visible and invisible, and the fact that as you orient this directionality from, say, left to right, velocity left, velocity right, that you would change what polarization would be absorbed and which would be not absorbed. So that's the difference between magnetism, is that the north side, the current is clockwise. The south side, it would be counterclockwise. Something that simple. And that's the nature of what can be absorbed, is based on the fact that depending on the angle of its interaction, clockwise is going to be different than counterclockwise. So yeah, I don't have a picture for that though. I have to draw that up. I have to work on that. It's just really hard to do the three-dimensional thing when you're basically saying that yes, as you move something, you're losing two of the dimensions, and the two dimensions though are pretty boring. So when you take the third dimension out of two, the difference between 3 dimensions and 2 dimensions is kind of a tricky one, because the 2 dimensions do seem rather connected. I mean, this seems so connected. I mean, up, down, left, right. I mean, this is just too easy, too simple. And it's from that perspective for each thing, though, because from this direction forward and back is just like up and down. It just turns into left and right from this direction, and this direction is the same. So the other 2 dimensions are much simpler from the third dimensional perspective. So whatever dimension you are sitting at, the other 2 dimensions seem incredibly simple. Up, down, left, right. They're flat and samey. But three-dimensionally, they're not flat and samey. Okay, really, that is not exactly the way I want to say it. There was different ways of visualizing it, but I tried doing it with the sphere, and you just you draw the arrows for the sphere. Okay, so you have a circle, and so you have these 2 arrows going this way and an arrow going that way, representing. And then you could add the other dimension, which let's see would be this way. And so you have those arrows, which you could also draw as arrows going the same way. So I mean, this going around is doing the same arrow direction as this. So the arrows seem similar until you add the third dimension, and then you end up with arrows going up and down. So if you see what I mean, is depending on where you orient, where you start with, what dimension you're drawing from, two of the dimensions seem very similar in that their directionality is the same in a sense, and it's only this third dimension that is different than the other two. But clearly it's like that from each dimension's point of view. There's not some special dimension that's the third dimension. It just happens to be whatever dimension's moving we'll call the first dimension, and the other two are the other two dimensions. But the other two dimensions have a similarity distinctly different than the dimension that's moving, no matter what dimension is actually doing the moving. Yeah. I mean, there is no up, down, left, right, forward, back until you select one and declare it to be something. Then they all have an identity. Okay, so yeah, so there's no, I'm not really ready to complete this argument, but I'm just saying that this gives me some indication of how polarization actually happens, is that it's a byproduct of what happens when you move the electron and you start to break up the up, down, left, right dimensions to do the forward thing, that you create this opportunity to absorb and release, and that through that process that the field energy is polarized. Now, how that, like I said, the specifics of the absorption of that polarization and why it is invisible or visible depending on polarization, I'm not really prepared to go into an explanation of why there's a distinction, because I have to think about that. But that's what, it's not that I'm saying that there's no problem, except that it's conceptually complicated. So you have to come up with a picture of it, a drawing, or some way to explain it. I just don't have that at my fingertips. But I don't mean to imply that I have some question about it. It seems certain that the mechanism exists, and that the mechanism is related to the velocity of electrons. The faster the electrons move, the more they polarize, the more magnetism or charge created. So it's just about the velocity of elements of matter, and the velocity of elements of matter really just means what percentage of the matter is now imbalanced. It just really means how much of the material structure has moved from the matter to the field around the matter. Its identity is now represented as the field, and it's only through expanding and collapsing that field that it gains acceleration or gives back or loses acceleration. So as it decelerates, that field contracts back, puts back the identity of the matter, the dimensional identity. Some way to say it. It rebalances the energy, the mass. So now the mass, when it's accelerating or has velocity, the mass is now disproportionately in a direction. There's more mass as I move. There's more mass in this direction than I have mass in the other directions. I weigh more in this direction. And as I slow down, I start to weigh less in the direction I'm moving, and my other dimensions gain mass. So my overall mass profile changes. That's probably the way to say it. Okay. All right. So I think it's, hopefully you get what I'm talking about. But really, this velocity thing is critical to the polarization thing. That's what creates the polarization, is the velocity of electrons. And it seems to me a fact that magnets must be they have a what's the word I'm looking for? Current inside of them. A lossless current. They don't make heat. They're a perfect conductor, so to speak. Superconductor. Let's see. So, what do I want to do with this? I just a curiosity. So this is it used to be a magnetic hook, right? So the magnet's not in there anymore. Magnet's on here, actually. But this was sort of interesting, is that, you can pick up the ball. Okay. Stay where you were, please. So, that you can pick it up. Okay, so magnetism is being induced into this thing to allow it to pick that up. And then as this gets further away, this steel loses its magnetic effect and the ball falls. But it's just kind of funny that here it's a powerful enough magnet to hold the ball, but it's not, as soon as I get far enough away, it's not magnetic enough to hold it, and yet this magnet isn't strong enough to push it back down. So I think that's sort of interesting. So this big powerful magnet down here can't hold the ball because this magnet's strong enough to hold it. So the ball's caught underneath, and then as I get further enough away, so it's just completely opposite from your intuition. You'd say, well, as this gets further away, this magnet gets weaker and weaker, and there shouldn't be a problem. But it's that this magnetism is completely induced. See, it has no magnetism. It's only magnetic when it's in a magnetic field, and it's repulsively magnetic, which is interesting too. See, it's right here. It's not really attractive. It's kind of mostly repulsive, and it's only when it gets in certain positions that it's attractive. But it is quite interesting that I just noticed that was a real example of the induction thing. Is the magnetism is just being induced temporarily while it's in the field. So when it's in the field, it's absorbing the current, what's being expelled from the internal velocities of the electrons. And so anyway, it's quite interesting. Anyway, got lots of different kinds of magnets here I've been playing with. It really is quite. I need more time to do it right. Anyway, quite interesting. But even just playing with different magnets, and they do all kinds of stuff. And stop it! They really are like animals after a while. Anyway, so enough of that. So till next time and such, so forth and whatnot. I really got to do some writing. I really just don't want to write this stuff, but I got to do it. Anyway, till next time.